The big one is ASM. That's the one most people will be using, and that's why I want to talk a bit about it now. ASM is, in effect, it's a logical volume manager. You take physical volumes and assemble them into logical volumes. Those of you with a system administration background, you'll know exactly what I'm talking about. It's like RAID. Multiple physical devices, assemble them into one logical device, and your files are striped and mirrored across the physical volumes that make up the logical volume. But the ASM file system is optimized and oriented for database storage. You can't put your processing files on an ASM file system, only database files. Unless, previous slide, you go for ACFS on top of it, of course, that's a different matter. So what are your ASM disks? Well, the one thing they are not is disks. That's the one thing they aren't, disks. When ASM first appeared in 10G, you could actually use whole disks for ASM. You can't anymore. You can't anymore. You have to use, if you're going to use disks, directly attached disks, they have to be partitioned. They have to be partitioned. And what you do is you cover the whole disk with one big partition. Directly attached disks, just a bunch of disks. Alternatively, you can use a SAN. That means going through host bus adapters, fiber optics to LUNs. So you'll be using LUNs as your ASM devices. So you might ask your system administrators to give you 8 1 terabyte LUNs. And you assemble those 8 1 terabyte LUNs into an 8 terabyte ASM disk group. And ASM will then stripe and mirror across the 8 devices. The underlying storage for those LUNs could itself be RAID, of course. And that's very good indeed, because then you have 2 levels of striping. Your SAN is striping the volumes, which means you're presenting high-performance volumes to ASM. And then ASM will then intelligently stripe its files across the RAID volumes. 2 levels of striping, best for performance. Maybe, maybe. You can use network-attached devices. I like these. Again, as I said, I liked NFS. You can use these things because I understand them. That's why I like them. iSCSI devices. So they look to Linux or Windows just like directly attached disks, but in fact they're remote devices and you're getting to them with TCP. You can use NFS files on an NFS server. Rather than using NFS directly, you create big NFS files, pad them with zeros, and use them as your ASM devices. Nice solution. Nice solution. But whatever solution you're using, you've got a problem with operating system permissions. Take a look at this. On this device here, Alice Meyer said, this machine here, /dev/SD star, I've got SCSI disks here. SCSI disk A, owned by root. SCSI disk B, owned by root. C, owned by root. D, owned by root. And then E, also owned by root. Those are my SCSI disks. I'm using SDB, C, D, and E for ASM. So I've covered the entire disk SDB with one partition, SDB1. I've covered SDC with one partition, SDC1. And that partition, look at its ownership, Oracle DBA. That's interesting, isn't it? You need a way to make sure the Oracle processes can read and write the devices you're going to use for ASM. Because by default, of course, as you can see here, my SDA devices, they're all root-owned. And it's only because they've got a file system that I can actually read and write things on SDA. Important point, that. So we need a mechanism to ensure ownership of devices. How do you do that? Well, under Linux, you've got 3 basic techniques: ASM lib, ASM filter driver, or UDEV. Historically, people tended to use ASM lib, and many people, including me, never liked it. And people like that, such as me, were often happier to use UDEV. Your system administrators may be happy as well because they understand UDEV. In release 12, we've now got the ASM filter driver, which replaces ASM lib. If any of you are still using ASM lib, think about replacing it with the filter driver. It's better technology than ASM lib. If you're not using Linux, there'll be platform-specific techniques.
Pardon, John. Which is better? Is there a which is better, or is there one that's better over the other?
Right, with these three here, ASM Filter Driver is definitely superior technology, but I don't think, this is me speaking, not Oracle speaking. I'm not personally convinced the ASM Filter Driver is production ready. I definitely think it's better than ASM Lib, but I think for the time being, I might be happier to stay with UDEV. UDEV is rock solid, reliable technology. ASM Filter Driver is still a bit new. Basically, when you install your clusterware, you can't install ASM Filter Driver. You have to build the cluster using either ASM Lib or UDEV, and then replace the ASM Lib and UDEV configuration with Filter Driver. And that tells me it's not quite there yet. Right.
And in the queue,
but that's only me speaking, not Oracle.
And in the queue, if JBOD is used in ASM, does that imply that data is or can be loosely coupled?
I'm not quite sure what that means, but I would suspect the answer is no. Oh, I see the question. The Oracle Data Appliance. No. The ODA, going back to the previous slide, ODA uses JBOD, directly attached devices. That's what you get in ODA. Oracle is absolutely clear that directly attached devices give you the best performance. I say Oracle is clear on this. This is undoubtedly debatable. But with ODA being an engineered system, Oracle claims to have balanced the I/O rates of the disks, the I/O capacity of the disk channels. And Oracle claims to have balanced all steps in ODA, so that using directly attached storage really will give you maximum possible performance. That's Oracle's claim. So ODA uses JBOD. The JBOD, the disks, they're just a bunch of disks, are covered with big partitions, as I've done here. And the partitions are then assembled into ASM disk groups. And the ASM disk groups are then used as backing storage for ACFS clustered file systems. So there's multiple layers in ODA that you've got. On top of ASM, you've got ACFS file systems. The point of that is that the DBAs and the users just see what looks like a perfectly normal file system, and they're shielded from the possible complexity of ASM beneath it. We, of course, the administrators, have to know what's going on. Okay, so that's our storage cluster. You need some sort of technology to get this thing shared and usable. Now, having done that, finally, we can build a database cluster. The database cluster, I'll put my database cluster in red. On node 1, we have an instance, which I shall call I1. It's an SGA and a bunch of background processes. On node 2, we've got an instance, which I shall call I2, which is a block of shared memory and the usual background processes. Now, the two instances talk to each other across the interconnects. There are processes that will, in effect, ping across the interconnects to find each other. That's necessary so that the database instances can build up the database cluster topology. And guess what? On disk is the shared database. You've got your data files, you've got your online log files, and you've got your control file. Multiple copies of it, probably. Now, within the control file structure, there is, in fact, within the control file, a structure that is written to by both instances. And that's pretty much the only difference between a RAC's database and a normal database. The control file is slightly modified. And both instances, or 16 instances, talk to each other across the interconnect to build up the topology of the cluster, and they write to the control file structure their impression of the cluster. And you can draw an exact analogy with what the clusterware daemons are doing. Because it is possible to have what you might call a split brain between the instances. If for some reason I1 loses contact with I2, but they're both still running, then they won't be cooperating when they use the shared resources, which are the data files. So you need that control file structure as a secondary means of communication to ensure that the network communications really are valid. And that's your major bit of theory. The layers of clustering. Hardware cluster, operating system cluster, storage cluster, database cluster.